Sorry guys, I lost audio there for a second, so I'm not exactly sure where it cut out, but I think I'm back. A simple curve never intersects itself. A closed curve can intersect itself. So I could come along, I could come back, and it has the same start-stop point. You could also go along, come along, come along, come along. Okay, now that actually, we have a starting and a stopping point that are the same. So sometimes with, I could come along here. This is a simple closed curve. All right? So that's what we mean by a closed curve. Now, if we keep looking, we want to take a look at what we mean by a polygon. We are going to spend quite a bit of time analyzing polygons. The prefix poly means many, so we're looking at a many-sided closed curve. Many-sided. So we're going to have some line segments. And we will look at specific polygons in just a moment, starting with 3 sides, etc. Okay, many-sided closed curve. And then there's 2 terms that we look at quite often when we're describing a polygon. It's either convex or concave. Okay, so this is a convex polygon, so it has many sides, but any 2 points on the interior can create a line segment wholly contained within the figure. A lot easier with a picture, but if I take any 2 interior points, okay, the line segment they create, line segment created, oops, okay, the line segment created, I'm trying to switch pens, stays inside the polygon. Now, if it's concave, if I take 2 interior points, the line segment may not stay within the polygon. Any 2 interior points create a line segment which does not stay on the interior. So we may end up with something outside. I'm going to just say similar, does not stay on the interior or on the inside of the polygon. So let me draw pictures of these. Convex, concave. So an example of a convex polygon might be come around, come outside, where it doesn't matter what 2 points I choose. If I pick any 2 points within the polygon, the line segment stays within the polygon. If I pick any 2 points within the polygon, that line segment stays inside the polygon. However, if it's concave, perhaps I go out here, it's still a polygon because it has many sides, many line segments. As soon as I can create a line segment given 2 points, but that segment ends up on the exterior part, that's called concave. So I think of it as a cave goes into the mountain, So if I ever have a portion that comes back inside, then that's concave. All right. So let's take a look at some of the types of polygons that we can have, and the most common that we will see. So let's go over their names. Names of polygons. All right. Because polygons, many-sided figure. And I'm pretty confident you're familiar with some of these names, but perhaps not all of them. So since we just talked about polygon being a many-sided closed figure, I'm just writing it again. Let's talk about what we have and what we call them. So we'll make a little table. The number of sides and the name of the polygon. Well, the smallest polygon we can have, let's think about this logically. You don't have to write this down. Don't write this down. If I have one side, it's not a closed shape. If I have two sides, again, it's not a closed figure. So the smallest polygon we can have is a three-sided shape, which we call a triangle. Prefix tri meaning three. Then if we have a four-sided shape, well, start asking yourself, what's that called? Some of you say square, somebody else might say rectangle, somebody else might say rhombus, trapezoid. We actually call it, any four-sided shape is called a quadrilateral. Quad meaning four. Lateral means side, so it has four sides. Five sides, we have a building in Washington. Five sides, called a pentagon. Six sides is a hexagon. There's an X in hexagon, there's an X in six. Seven is what we call a, heptagon. 8, octagon. 9, nonagon. 10, deca, like a decade, decagon. Sometimes you see it spelled with a C, sometimes you see it spelled with a K. Right? Either way is fine with me. 11 is what we call a hendecan. A hendecagon. Sorry, that's H-E-N. The pen's erasing itself. Let me try a different black pen. 12 is what we call a dodecagon. And pretty much anything after that, it's just like if it's 15 terms, it would be a 15-gon. 16 terms would be a 16-gon. 20 terms would be a 20-gon. So we just call that an n-gon. All right. So now once we have these polygons, let's take a look at some of the vocabulary associated with polygons. And polygon just means any multi or many-sided figure. So let's take a look at some vocab given a polygon. So I'm going to draw a quadrilateral. It's not going to be a square on purpose or a rectangle on purpose. It's just going to have 4 sides. But I'm going to extend one of the sides so that we can discuss what that might be called. So, I'm not making it any specific length, you guys. I'm just sort of drawing a 4-sided figure with one side that has been extended. And I'm going to call this figure vertex A, vertex B, vertex C, vertex D. And then I'm going to call angle A, angle number 1, and this part of angle D is angle number 2, so that we can just discuss some of the vocab and descriptions. So one of the things we want to take a look at are what we call consecutive angles. And consecutive just means things that go in order. Consecutive days of the week, Monday, Tuesday, Wednesday, Thursday. Consecutive angles are angles which go in order. So for example, if I start with angle A and I go clockwise, if I start with A and I go clockwise, I could say one example might be angle A, B, C, and then D. A, B, C, and D are all consecutive angles. But somebody else might say, well, I don't want to start with angle A, I want to start with angle D, and I want to go counterclockwise. So maybe you start with D and then C, B, A. But the idea is they're the ones that are next to each other. Another example could be, well, angle A and angle B are consecutive because we're just going in order. And we also have consecutive sides. And again, those are the side lengths, or the sides that are going in particular order. So perhaps I'm going from A to B, and then B to C. So examples of consecutive sides might be side AB and BC. Or I could have side AD, now you have a choice. I could go AD and AB, or I could say AD and CD, or DC. AD, DC. And that's what I mean by consecutive side. There's more pairs, but I just want to give you the idea that they're next to each other. They're in order as you go around. And then let's talk about the angle placement. We have what are called interior angles. And we have exterior angles. So interior angles are angles that are on the inside of the figure. So examples of interior angles. Well, we could have angle A or B or C or D. Angle A, angle B, angle C. Now this one's kind of tricky because it looks like there's 2 different angles there. So maybe I say angle ADC. Or I say angle ABC. Since B is in the middle, that would be the vertex. I could also say angle 1, because I did list one of them by a number. So anything that's on the inside. Exterior angles are on the outside of the polygon. So these are angles on the outside of the polygon. To create an exterior angle, we extend one side. Okay, so we extend one of the sides. So in this case, I took side AD and I just extended it. So you'll notice angle 2 is having a vertex of D, but it's on the exterior part, it's on that extension. So an example, I only gave you one in this case, is angle 2. I'm going to create another one right now, and we'll call it angle 3. If I take and extend one of these sides, let's see, for ease of picture and what will fit in our diagram here, I'm going to extend side AB. Okay? And now I've actually given you another angle, because now angle B has part that's on the inside, but there's this other part that's on the outside, so I can call that also an exterior angle. Okay. So now that we've talked about some of the parts and pieces, let's look at what happens when we have side lengths or angle measures which are the same. So we're going to take a look at the word congruent. Because we don't always want to say they're equal, because equal has a variety of meanings. So when we're talking about geometry and we're talking about the angle measure or the side length, we refer to the term congruent. All right, so the definition of congruent. Congruent means equal in measure. Congruent has a symbol. The symbol for congruent is an equal sign with like a squiggle above it. So say, for example, I give you this triangle. Switch. And let's say I give you this triangle right here. Just going to make this up and call this triangle ABC. And I'm going to tell you the measure of this interior angle is 60 degrees. And then I'm going to give you this other triangle. We'll call it DEF. And I'm going to tell you that this angle E is 60 degrees. So what I would end up saying is, okay, a couple ways I could say this. I could say the measure of angle A equals the measure of angle E. But instead of having to say all of that and forgetting maybe what the little m means, instead I could say angle A is congruent to angle E. So that congruent symbol just means I know they both have the exact same measurement. Similarly, let's say I have that side length CB is 4 and EF is 4. Okay, well, now if the two sides have the same measure, I could say that they're also congruent. So I could say the measure of line segment from B to C or C to B, it doesn't matter, is equal to the measurement of line segment EF. But instead of having to say all of that, I could say that side BC is congruent to side EF because they have the same measure. All right? Okay. So anytime we use the equal sign, anytime we use this equal sign, we're talking about the same measurements. And of course, EF is the same as FE. So it doesn't matter that order. So now let's take a look at some, I know. Let's look at this definition. I don't want to forget this before we make a chart. The definition of a regular polygon. So now we're fine-tuning what you've seen growing up. If something is regular, it is said to have the same measure, meaning all angles are the same measure, all sides are the same length. So regular polygons are equiangular, so they all have equal angles, angle measures. So they're equiangular and, oh goodness, my pens, I'm going to have to go out to the other room here, I think, and get more pens. And equilateral. Equilateral. Lateral means side. So this would be equal side measures or lengths. So if something is regular, it is both equiangular and equilateral. So let's look at some common shapes that you may be familiar with. You may have heard of them, but I want to make sure you guys that we are specific in how we actually describe them. Okay, so well, I'm trying to figure out which way I want to do this first. If I want to go, we'll just go in order. We talked about polygons. Let's talk about our smallest polygon. Let's say I give you this one. And I'm just going to tell you this is triangle ABC. And I'm going to tell you that all three angles measure 60 degrees. And if I were to ask you in person, I'd say, hey guys, what kind of triangle is that if all three angles are the same? Oftentimes I would hear people say, oh, that's equilateral. Well, careful. Yes, but the only thing I gave you were the angles. So in this case, this is what we would call equiangular. It's equiangular because all angles are equal. Now there are some theorems in geometry that we haven't gotten to yet, base angle theorems and various things. But if I tell you that, let's say I tell you that I have this side is congruent to this side, which is congruent to this side. So I put a little mark. The marks are identical to show that the side lengths are the identical measure. Now I could say that this is also called equilateral because the lateral sides are all the same in length. Okay, so we have equiangular, equilateral. Let's say I give you something like a square. Let's describe a square. I'm sketching it instead of grabbing a protractor and a ruler. Is a square regular? Well, in this case, yes. Equiangular because each one of these corners is 90 degrees. right? Each one's 90 degrees, therefore it's equiangular. And then a square also happens to be equilateral. All four sides are congruent, so it is also equilateral. Now we can keep going, and I'm going to show you something here in just a moment, because we can make a regular hexagon, a regular pentagon, a regular octagon. The idea is something is considered regular if all sides are the same measure, all angles are the same degree. So I want to show you how to calculate what those angles are. So what we want to start with is the angles that are in a triangle. And if you remember this, then you can do all of them. So the first thing I'm going to give you, and we're going to do this with a piece of paper and a pair of scissors. So once you get your scissors and your piece of paper together, this is a really interesting and cool thing you can show any class at all. I'm just going to start with a piece of paper, okay? And oftentimes I'll have pre-cut paper for them to experiment with, but just watch this for a minute. Here's an easy way to calculate how many degrees there are in a triangle. I'm going to take and I'm going to make a triangle. In fact, I think I'm going to make some very large triangles, maybe some small triangles, but because this is on video, I think I'm going to keep them rather large. And you can see all I've done is cut 3 different size triangles. Okay, maybe some of you are like, oh, I don't like that one. They have 2 right angles. So here, I'll make this one not right. Oops. Better make it a triangle, though. Okay. All right. I'm going to take one of these triangles. I'm going to use the largest one first just to show you because it might be the easiest one to see. And I can see that I have 3 vertices. I'm going to name one of them angle number 1, one of them angle number 2, and one of them angle number 3. Order doesn't matter. And then what I do is I show the students, okay, take our 3 angles, and we want to add them all up. So I'm going to tear off, here's angle number 1, here's angle number 2 and angle number 3. And if I add them together in any order, I'm going to take angle 3, put it right next to and add it to angle 1, and come in here and add it to angle 2. Well, you'll notice what I've got and what I've actually created is this straight line, and we know a straight angle has 180 degrees. Well, what if I add them in a different order? And I take angle number 2, add it to angle number 3, and then add it to angle number 1. Again, you'll notice that all 3 angles add up to a straight 180 degree angle. Well, some will go, well, that's because that was a right triangle. You started with a right triangle, teacher. Okay, let's start with a triangle that does not appear to have a right angle in it at all. Okay, well, if I do the same thing, call one of the angles angle number 1, one of the angles angle number 2, and the other one angle number 3. Again, have the students tear them apart. You can tear them apart. There's angle number 2, angle number 1, angle number 3. Have them add them in any order at all. And what we'll find is, no matter how you add those 3 angles together, you will always create a straight edge or 180 degrees. So it's a really nice little technique. Instead of just telling them, oh, trust me, trust me. Because oftentimes it's like they don't know where it came from. They just know, oh, I'm supposed to memorize this because my teacher told me to. So we now just showed that the measure of any triangle at all is 180 degrees, the sum of the angles. Okay, so I'm going to make a note of that. Note. Okay. The sum of the interior angles of any triangle is 180 degrees. Now, why does that come into play? Well, no matter what shape I give you, you can always figure out the interior angle sum. So we'll be able to figure out some of the measurements if they're regular. So what do I mean? Okay, let's say I give you a regular pentagon. And I ask you to find the sum of the angles, interior angles, of a regular pentagon. So the first thing we need to remember is, well, how many sides does a pentagon have? So a pentagon has 5 sides, right? If it's regular, I've got to make all these sides look somewhat the same. So I'm just going to get 1, 2, 3, 4, 5. Make it look kind of like a house. And if I want to figure out what the sum of all these angles is, yes, there's a formula. We can develop it. But I can also use the fact that any triangle has 180 degrees. So if I take my pentagon and I break it up into triangles, I'm going to go, well, I'm just going to pretend I have a triangle here. Well, now I have 180 degrees in that triangle. If I put another diagonal in, I've created another triangle, so there's 180 degrees in that triangle, and there's 180 degrees in this triangle. So for a pentagon, I get 3 times 180 degrees, which is 540 degrees. So if I were to counter off of that, I'll call this part A, I'll call this part B. Find the measure of each interior angle of a regular pentagon. Okay? Well, we already figured out the total sum of all the angles. The total sum is 540. So I already figured out the total sum Now all I need to do is divide it by the number of sides. In this case, number of angles. Because we want all of them to be the same. So we would end up with 540 divided by our 5 sides, which ends up being 108 degrees each. And this will work for any shape. We can try it again. All right? We could take, let's see. Let's say we take an 8-sided figure. I'm not going to try to make it regular. Let's just take an octagon. Find the sum of interior angles of an octagon. So we've got to try to draw an octagon. 1, 2, 3, 4. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8. All right, maybe not perfect, but it worked. And I want to know what's the total number of degrees in this octagon. So we know that there's 8 sides, which means that there's 8 angles. But let's figure out how many triangles we could break this up into. So I'm going to draw what are called diagonals. Diagonals go from any vertex. On the interior, it's this any vertex to any other vertex. So I see one triangle. I'm going to just stay at that same vertex and go across. Eyes go to this vertex. There's another diagonal, a second triangle. I see now 3 triangles, 4 triangles, 5 triangles, 6 triangles. So I notice that because these are all triangles, this has 180 degrees, 180 degrees, 180 degrees. I think you have the idea. So in this case, we would end up with 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So we had 6 triangles. So that's 6 times 180 degrees. And what is 6 times 180? Sorry, I should have been a little more prepared. 6 times 180. 1,080 degrees total. So now if I ask you, all right, then find the measure of each, find the measure of each angle, interior angle, of a regular octagon. So because it's regular, we know that all 8 angles need to have the same measure. All right, so if we now figured out that there's 1,080 total, we would take our 1,080 degree total and divide by the number of angles in our polygon. It's an octagon, so there's 8. So if I take my answer, divide by 8, I should get 135 degrees per angle. All right, so we do have a formula for that. So to calculate the measure of the interior, so we do have a couple calculations. To find the measure of the sum of the interior angles, of any polygon, take the number of sides minus 2 and multiply by 180 degrees. Therefore, if we now know how to find the total sum, then to find the measure of each angle of a regular polygon, okay, the measure of a single angle of of a regular, it's got to be regular, well, we've got to find the sum first, and now divide by however many sides, aka however many angles there are for that regular shape. Okay. So we can classify triangles by their angles. We can classify triangles by their sides. We also can we can classify certain quadrilaterals by what characteristic they have. So I want to take a look at some of those. We said it earlier, but I don't think we've written it down. So let's take a look at triangle classification. Actually, there's a great chart. I'm trying to think of, you know what? We'll do it this way. I could write down this exact same chart, but what I recommend you do is classification of triangles and quadrilaterals. Because we have different kinds of triangles. We have acute, obtuse, scalene. Then we also have equilateral, isosceles. Okay. So, no, I'll go through some of them with you, but these all can be found on page 644 to 645 in a lovely table that you definitely want to look at. Actually, you know what? I am going to let you look through this table, and then if you've got some questions, we can discuss that in class as to what's the difference or etc. So I'm going to let you actually look at that first so that we can finish up here with some symmetry and a little bit of rotational symmetry. So I recommend you copy down the shape and what makes it that shape, since the book has a very nice chart of how to do those. All right, so let's finish up with some symmetry and what it means to be symmetric. Okay, so symmetry. We have different types of symmetry. We have line symmetry, and we also have what are called rotational symmetry. So we have line symmetry, which means if I were to draw an imaginary line, an invisible line, a dotted line, okay, that's not part of the shape, through the figure, would it reflect and would it look exactly like a mirror image? So symmetry is like a mirror image, all right? So lines of symmetry. You may have in elementary school the classic, here I have a little bit of this paper left, is, here's a piece of paper, okay? In elementary school, oftentimes we teach students, okay, if I want to make a heart for Valentine's Day, or I just want to make a heart, I'm going to fold a piece of paper in half. So I have this line that goes right down the middle of the piece of paper. So here's this line that goes right down the middle of this piece of paper, the fold line. And if I take that piece of paper and I fold it, well, now I'm going to cut out a heart. Okay? I'm going to start, I'm going to come around. Well, I don't actually have to cut the entire heart out because since I have half of it, as soon as I open it up, I have a shape that is symmetric about this line, this vertical line. or this diagonal line, or this horizontal line. So a nice way to talk about symmetry is the invisible line that goes down a shape so that when you fold it over, it matches up exactly. Okay? Pre-calculus, calculus, we may have called this even because it reflects about the y-axis. All right? So there's an example of a line of symmetry. That line is an invisible or imaginary line which the graph reflects about. Has an invisible line of symmetry which the polygon in this case okay, so it absolutely creates a mirror image of each other. And this line can be vertical. It can be horizontal. Because I could honestly turn my shape this way. It could be some sort of diagonal line. Okay, so I could go diagonally. Now we also have what is called point symmetry. It's rotational symmetry. Rotational symmetry. About a point. So it's rotational symmetry about a point. So sometimes it's like, think of putting a thumbtack in the middle of something and then going around it from there. So an example of that, actually, let's get clever here. I could get very clever and I could, oh, that might be a little off. I was going to say maybe I'll just sketch instead. If I think of an equiangular triangle, okay, if I think of an equilateral triangle, so okay, so here's an equilateral triangle, equilateral. All sides are the same. It also happens to be equiangular with all angles the same. Well, if I ask you if it has symmetry, you would need to check both. Does it have line symmetry? If I take a line, and I'm going to use my straight edge right here, and I put a horizontal line through my shape anywhere, okay, and I don't know how well this is showing up, but if I put a line through here, does it look like it's the exact same shape on both sides of this line? And the answer to that is no. If I fold it in half, it would not look like itself. It wouldn't be a mirror image. What about a vertical line? Well, could I, if I put a vertical line through here, would it fold over onto itself? And the answer is yes. So it does have line symmetry. But it also has, and what I wanted to look at is rotational symmetry. Imagine you put a thumbtack right in the middle of this shape, okay? If I put a thumbtack and I rotate this either counterclockwise or clockwise, is there a point at which it will land right on itself? And the answer is yes. So this has rotational symmetry. It's as if you have just spun it and it landed on itself. So a rotational symmetry, you're going to need to tell me the degrees that it rotates. So we have to talk about between 0 and 360 degrees. So it looks like in this case, this is going to rotate 120 degrees because there's 360 divided by the 3 angles, 120 degrees, and I should land on the next shape. So that's what we mean by rotational symmetry, okay? So you're going to be looking at pictures that have both and trying to classify. Okay. All right, then until next time.